When we talk about the economy, we usually think in terms of lines on a graph, right? Inflation goes up, unemployment goes down. But what if that's basically like trying to understand a massive mountain range by just looking at a flat map? Today, we're going to explore a really different, kind of radical new way to see economic data, not as flat lines, but as solid three-dimensional objects you could almost hold in your hand. So let's dive in.
I mean, for decades, our whole view of economics has been shaped by two-dimensional tools. Now, don't get me wrong, they're useful, but they're stuck in this flat world, showing us how things are related in a very, very simplified way. Okay, take the famous Phillips curve, for example. For more than 60 years, it's been the go-to diagram for showing the trade-off between inflation and unemployment. It's this simple, elegant curve on a 2D plane. It's been a huge cornerstone of macroeconomic policy. But this is the big question, the one that drives this whole new approach. What if that elegant flat curve is just a shadow of the real story? What are we really missing by staying in just two dimensions? Right, so here's the problem. These flat models are just static snapshots. They can't really capture the depth, the passage of time, or the sheer magnitude of economic forces. That's kind of like trying to describe a hurricane with just a drawing of a bent arrow, right? You miss the real power, the intensity, the sheer volume of the whole thing. So, to get around this flat world problem, researcher Mario Arturo Ruiz Estrada came up with this, pretty groundbreaking idea. What if we took those flat lines and just gave them a third dimension? And that brings us to what are called solid economic prototypes, or SEPs for short. The core idea here is to turn abstract economic data not into a line, but into a tangible, volumetric 3D structure. It's like going from a 2D drawing to a 3D sculpture. And believe me, that changes everything. So this is the huge leap we're talking about here. Instead of just static lines on a page, we get 3D solids that have volume and depth. And with that, we can go beyond just seeing a relationship to actually, feeling its tension and intensity, all represented in a physical form. Okay, so that all sounds pretty cool in theory. But how do you actually turn a 2D curve into a 3D solid? Let's walk through how they build one of these, and we'll use our old friend the Phillips curve as the perfect example. The whole process is this really fascinating mix of art and science. First, you start with the original data, then you actually manually build a physical mock-up to give it some shape and volume. And from there, it's all about using photos and AI to create a really clean digital version, and then refining that into the final polished object. All right, so step one, you start with the foundation, the familiar, classic 2D Phillips curve. This is basically the blueprint for the whole thing that's about to take shape. And then the magic starts to happen. They build a physical mock-up, maybe out of paper or clay or something. And all of a sudden, that flat line has depth. It has a real physical presence. You can see how the relationship isn't just a line, it's a surface with actual contours. Okay, next up, technology takes over. A picture of that physical model gets fed into an AI, which cleans it all up, smooths out the edges, and it turns that rough concept into a really clean, high-res digital object. It keeps the original structure, but makes it ready for some serious analysis. And boom! Here is the final result, a polished, high-resolution, solid Phillips surface prototype, which the creator calls an SPSP. It's not just data anymore. It's a physical thing that represents all those economic forces, with a shape and a volume that tells a heck of a story. All right, so we've got this beautiful 3D object, but what in the world does its shape actually tell us? How do we read this totally new kind of economic landscape?
Well, reading it is surprisingly intuitive. Just think about it like the difference between a calm pond and a stormy sea. A stable economy? That makes a small, compact, smooth-looking solid. But an economy under a lot of stress, what the author calls economic depredation, that creates a big, expanded, really spiky shape. The geometry itself becomes this powerful diagnostic tool.
Okay, let's put this to the test with a real-world example. Malaysia's economy from 2012 to 2022. Now, based on what we just talked about, just take a look at the shape of this thing. What's your gut reaction? Stable or not so much?
Well, according to the analysis, the conclusion is pretty clear. The author says it directly. Based on the shape of its prototype, Malaysia's economy during this time shows all the signs of high tension, or economic depredation.
And you can totally see why. I mean, look at it. The model is big, it's tall. It has these sharp peaks that suggest some strong, sudden tensions between inflation and unemployment. Its sheer volume points to these constant pressures. And those jagged transitions show an economy that's really sensitive to shocks and gets disrupted a lot. The entire story of the economy is literally written in its geometry. So look, this is way more than just a fancy new way to make graphs. Moving to 3D really opens up a whole new dimension for how we can analyze and even talk about economics. So why does this really matter? What's the big deal? Well, because it makes these abstract economic forces tangible. I mean, just imagine putting the solid model for a volatile economy right next to one for a stable economy. The difference would be instantly obvious. You could physically see it. It turns abstract ideas like macroeconomic tension into something you can see and rotate and actually understand, which makes it this incredible tool for students, for policymakers, really for anyone trying to get their head around the true shape of our economy. And that leaves us with a really fascinating final thought. This whole method was applied to economics, but it just makes you wonder, right? What other complex systems in science and sociology, maybe even in our own lives, are we still looking at in only 2 dimensions? What crucial depth are we missing by looking at the world like it's a flat map?